Yeah, thanks. So today, I'd like to talk about higher-order type-level programming in Haskell. So just a quick show of hands. How many of you have used type families or any type-level programming facilities in Haskell? OK, that's most of you. How many of you have been annoyed that you can't do higher-order type-level programming? Great. So hopefully, this talk will make you even more annoyed that you can't do it today. But there's a solution. So before we get into deep technical details, let's just do a quick recap of Haskell 98 features, because before we run, we need to learn to walk. So Haskell 98 has these types and type constructors like int, maybe, and either. And as you can see, they come with these kind signatures. So int is of kind type. So the kind type represents values that can be inhabited at runtime. So like 5 inhabits the type int, which is of kind type. We have type constructors like maybe. So maybe is a type constructor because it takes a type and returns another type. So it has this kind type arrow type. And either is a type constructor that takes 2 arguments. So it takes a type, another type, and returns a type finally. Now, something interesting, or something that is like we take for granted, is that we can actually partially apply these type constructors. So what I mean by that is we can not only ask for the kind of maybe on its own, or actually maybe is a bad example, but either on its own, we can ask what's the kind of either when partially applied to something like int. And as you can see, either partially applied to int will have kind type to type. So it's quite natural. It's exactly the way it works at the value level. So partial application is a very familiar thing that we can do in Haskell. And this is just to show that it works at the type level as well. Now, why is partial application important, or why am I talking about partial application of type constructors? Well, it turns out that we use this partial application all the time whenever we're writing everyday Haskell. For example, the functor type class, which I'm sure everyone's familiar with. So the functor type class is a higher kinded type class because it ranges over type constructors or types of kind type to type. And it has this fmap function that takes a function a to b and gives us back a way to transform an f of a into an f of b. Now, 2 examples of functors are the type constructors that we've just seen on the previous slide. So maybe, you can write an instance for functor maybe, and you can see that in the instance head here, we're actually partially applying maybe, or maybe appears in an unsaturated way. When I say unsaturated, I mean it appears without all of its arguments provided. And here in the instance functor either e is a partially applied or unsaturated type application. OK, so GHC Haskell, or actually just Haskell 98, uses this information, or uses this partial application of type constructors when it's doing type inference. So what I mean by that is when you have when you use the fmap function, notice we can just write fmap show on just false, and we don't have to provide any type signatures. I don't have to tell GHC that I'm interested in the fmap implementation for maybe, because it can just work it out from the argument type. So, oops, yeah. So this is undefined. Yeah, the idea is the type of foo is maybe string. So right. So we turned a maybe bool into maybe string. How did that do that? So GHC is doing type application decomposition. So what that means is whenever we start from a function like fmap a to b to f of a to f of b, GHC, when I give the function fmap an argument just false, it sees that this f of a part is instantiated with maybe bool, So now it's trying to work out what f and a need to be respectively. And because maybe bool is this type application, f of a has this type application form, it just pulls them apart and works out that, well, f must be maybe and a must be bool. That's the solution, right? So here's this decomposition happening here. And as a result of that, in the solution, f is a type constructor which appears unsaturated. So something that maybe we don't really appreciate whenever we just write Haskell programs on a daily basis is that type constructors are actually always injective. Every type constructor in Haskell is injective. And what I mean by that is we have a function int maybe, which in the context has an equality between maybe a and maybe b. And then it returns, the type of the function is it takes an a and returns a b. So we know that maybe a is equal to maybe b, and we go from a to b. And the implementation is written as the identity function, which means that actually GHC has to know that a and b are the same type, because the identity function takes the type and returns the value of the same type. So the way it works out is from maybe a equals maybe b, GHC deduces that a must be equal to b. And we can generalize this, actually. So on the previous slide, I had maybe a equals maybe b. Here we have, for all f, where f is a type constructor, we can write a function that, given f of a equals f of b, we can write a function a to b and implement it as the identity function. And the fact that this type checks tells us that GHC managed to deduce that a must be equal to b, and that is using the injectivity property of the f type constructor. So just to try this, we can, and I'm going to use type applications to instantiate the type of injective. So the way that works is I say, what's the type of injective when f is maybe? And let's say I apply it to false. Right, so the type of injective when f is maybe applied to false will be, of course, the return type is b. We know that a equals bool, so b must be bool as well. So this injective function witnesses the fact that type constructors are injective. Okay. Another property of type constructors, and this is the other half this is the missing other missing piece of the application decomposition thing that GHC does. So type constructors are generative as well, which means that whenever we know that some f of a type is equal to some g of b type, so in the context here we have f of a equals g of b, so GHC actually knows, by decomposing the application, it knows that f then must be equal to g. And the way we witness this in this case is we say f of int equals, so we go f of a equals g of b, we go f of int to g of int, and the fact that we can implement this with identity, it means that f must be equal to g, and indeed this type checks. So we can say what happens if we instantiate f with maybe, and we pass in just 10. Then the return type is maybe int. So g is deduced to be equal to maybe. Okay, so injectivity and generativity together, they characterize the property, or characterize type constructors sufficiently such that GHC can do application decomposition in a sound way. So to recap, injectivity means whenever f of a equals f of b, a equals b. And generativity means whenever f and g are generative, then f of a equals g of b implies f equals g. And notice that a and b don't actually have to be the same. So it's really only about the constructor side of things in case of generativity. And so so type constructors are both injective and generative, and so Richard Eisenberg came up with this term called matchability, which is essentially a way to characterize this application decomposition property of type constructors. Type constructors are matchable, which means we can match against applications of them. Right, so that was a quick recap of Haskell 98. In the rest of the talk, I'm going to still talk about Haskell 98, by which we're going to mean Haskell with these 98 extensions enabled. It's quite a long list. There's even more. So the point is that let's see what kind of things we wish we could do, but we can't because of this, because of what we've just seen. So where it gets in our way. Okay, so one of my favorite GHC extensions is the type families extension. And in this case, we have an associated type family. So we have a class called DB, which classifies types that can be turned into a database representation. So if you say, when you have an instance for DBA, you have to provide an instance for the DB type family, which associates with the type A another type, which is the database representation of that type. So I'm going to show an example in a minute. And then the toDB function is a way to convert the type A into its database representation, depending on what the type is. So quickly notice that if we look at the kind of DB type, it takes a type, right? So it takes the A, and it returns another type. So it's an associated type. So you might be thinking, okay, the kind of DB type is then type to type, and you're probably right. So here are a few examples. I took this from an enterprise code base. You can tell it's an enterprise code base because both the username and password are mapped to plain text. So here are a few examples of instances of the DB type class. And I omitted the actual implementations because of space, but every time you see a DB type username, you know that it equates to DB text. So the toDB function for DB username would take a username and turn it into DB text. And just to show that it works, we can actually evaluate type families in GHCI by saying :kind bang. So the bang will force the evaluation of the type family, and I can ask what does DB type username evaluate, and it gives me back DB text. And similarly, I can do DB type password, DB text. Great. So notice that this DB type family is not injective. So if we know that the DB type of A equals DB type of B, that doesn't mean that A equals B. So in the particular case of username and password, they both evaluate to DB text, but that doesn't mean that the username and the password types are the same. So just to go back, all type constructors are injective. So maybe A equals maybe B implies A equals B. But not all type families are injective. And in this particular case, the DB type A equals DB type B does not imply that A equals B. And that's the example that I showed with username and password. So how does GHC? So before I could say I instantiated injective with maybe, and it just automatically decomposed. It automatically worked out that A must be equal to B, so it decomposed the application. How does GHC stop us from doing something like, asking what the type is of injective, DB type, username, password? So what could happen here is we instantiate F with DB type, we instantiate A with username, and B with password, and we know that F of A equals F of B, so DB type of username, which is DB text, is equal to DB type of password, which is text. So we know that equality holds. So can GHC then tell us that username is then equal to password? No, it can't. So there's this restriction in place precisely for reasons like this. So for those at the back, this is saying the associated type family DB type should have one argument but has been given none. So this is the saturation restriction, which is in order to avoid being able to instantiate F with arbitrary type families, GHC requires that every time we mention a type family, it has to be fully saturated, or in other words, fully applied to every one of its arguments. So here DB type appears unsaturated because it would take one argument and we haven't provided any. So this is not allowed. And this saturation restriction is the reason why we can't trick GHC into deducing unsound equalities. So type families must be saturated. That's the lesson we've learned from this little example. Now, that's great. So that means we can't abuse GAC's existing type inference mechanism to derive unsound type equalities. But it also means that there are things we really wish we could do, but we cannot do due to this limitation. So I'm going to walk through an example where we would really want to be able to partially apply or to mention type families in an unsaturated way. So let's say that I'm writing a backend for this enterprise application, and I want to represent users as, so the user type is a type level list of an ID, a username, a password, an email, and some date. Because everyone uses type level lists to represent application types or domain types. So now we have this type level list. We want to actually have a value that that represents this type level list. And so for that, we reach for these heterogeneous lists. So we have an age list, which is indexed by a type level list of types. And it has two constructors, the nil constructor, which is an empty list, and this cons constructor, which takes a value of type A, an age list of type A's, and it gives you back an age list of type A cons A's. So an example of this would be our test user, Chris, an age list of user, which means that we need a field for every single item in the list. So we have an ID, a username, password, email, and date, and then finally the nil at the end. Now, one task that we might want to accomplish is to take this age list of user type and somehow turn it into its database representation. So we start from the type user, and for every one of these items in the list, we want to end up with the respective database representation. So if you remember, we had these instances, DB type, so DB UID, etc., which would then have the DB type family mapping these types. Okay, so the function that does this is DB user. It takes an age list of user and returns what exactly? Well, that's the type that we want to return, obviously. So I could just type out a type level list of the result, but that wouldn't be very modular because that means if I update the list user, then I have to go to this DB user and update the result list. So clearly, we want something like map, because map is, we use map all the time when we're writing term level Haskell code. So why not write map at the type level as well? So here we implement map as a closed type family. So map takes as an argument type family A to B. It takes as an argument a type level list of A's and returns a type level list of B's. And the implementation is exactly what it looks like at the value level, except that the function is uppercase and all the constructors are ticked. Okay, so that means we should just be able to say map DB type over the input list. Okay. So now reload. Oh, and not again. Right, so we try to map the DB type over user, but of course, this requires mentioning DB type without its argument provided, and GAC doesn't allow us to do that because the type family DB type should have one argument, but has been given none. So that's pretty sad because we just wrote this type family, we wrote this map type family, we tried to put them together, it just didn't work. GAC says no. So of course there's a solution. I wouldn't be talking that it wasn't. So the solution, and this idea is due to Richard Eisenberg once again. The solution is to distinguish in the kind system between type constructors and type families, because the whole confusion was that GAC had this saturation restriction for type families because it didn't want to allow us to use type families in places where it expected the type constructor. So naturally, the solution is to come up with an extension to the type system that somehow distinguishes between type families and type constructors. And this idea of matchability and tracking it in the kinds is quite natural. So what we're going to do is change the kind of type families so that they no longer mention the same arrow as for type constructors, but we use a different arrow. So as you can see, the kind of maybe remains the same kind as it was. So it's a type to type. We call that arrow matchable. The kind of DB type becomes type twiddly arrow type, and we call this twiddly arrow an unmatchable arrow. Great. So now that we've done that, we can go to the map type family and replace its function argument with the twiddly arrow, or the unmatchable arrow. And of course, in order to get this to work, we need to turn on a new extension, of course, Haskell 99, unsaturated type families. But fear not, we can stay in Haskell 98 because unsaturated type families actually implies type families. So I've got 99 problems, but type families ain't one. Okay. Right, so now we can come back to our little example, DB user from before, and implement, well, actually, we can now compile this function because, actually, I can ask what the kind of DB type is. Right, so the kind of DB type is type twiddly arrow type. And notice that this has changed from before because we enabled the unsaturated type families extension. So once we've done that and we've changed the kind of the argument of map, we can compile this. So I can now ask what the type of DB user Chris is, and it tells me that the type of that is DB int, DB text, DB text, DB text, DB date. Great, so that worked. Now, how do we actually implement this function is the interesting question. So what we really want to do is write a map function that maps the 2DB function over every element of the age list and transforms the type of the age list as we go. So to translate that into code, we want a function called agemap, and you couldn't really do this before because you couldn't map a type family together with the normal function at the same time. But now you can. So let's see what that function looks like. So you want to say, we'll take an age list of x's, and I want to return an age list of map of f over x's, and of course, we need to take a function as well. So what should the type of that function be? Well, the first approximation is it should be for all a to f of a, right? Because this function should be polymorphic. It should work on any type in the list. So it's not we can't just say works in ints or bools. It has to have this rank 2 type. Okay. So let's see if that works. In the nil case, I just return nil. In the other case, x cons x's, I return f of x cons agemap f x's. Now, this is not going to work because how should GHC know which type family f we call the recursion with? It can't infer it because map is a non-injective type family, so type inference cannot figure out what function you mapped over a list so that you ended up with the result list. So we need to provide, actually I'll call this one G, so to distinguish between the term level and the type level functions. So I'm going to call, let's say for all fa x's, we want to call agemap recursively with the type family f. Okay. Now the problem is, let's try to write it. So DB user would be agemap of DB type of 2 dB. And it gives us this error message saying, actually, 2 dB requires a dBA constraint, but this function for all a to f does not mention any constraints whatsoever. So we need to put the constraint into the function as well, which is to say we need to parameterize HMap by a type class, by a constraint. So for all C, F, A, X's, this function should work as long as every element of the list has an instance of some type class C, right? So we put the type application back in this place once again. And then we finally say that db type, the HMap should work on any list where all the elements have a db instance, and then we map the db type family over the element type to then work out which function we should provide, which is always the 2 db function, but that's overloaded based on the db instance. So we're almost there. GHC will tell us that, oh, you said that this function works on any element that has a C instance, but I don't actually know that every element in X's has a C instance. So we need to say that explicitly. We need to require that all elements in X's must have a C instance. And that's a quick type family, once again. This is my favorite extension I mentioned. So we take a list of types, and then we take a constraint which takes a type to a constraint, and we return a constraint. And all on the empty list is just the unit constraint, and all on a non-empty list of some constraint is just we make sure that constraint that X has an instance for C, and we recursively call ourselves. Okay, that compiles. So just to quickly explain what all does, all says, give me a list of types in bool char, and give me a type class like show, and I'll compute a constraint which says that every element in this list must have an instance of show. So we have a show int, a show bool, a show char, and then the trivial unit constraint at the end. Great. So this is the true form of the map function. We can now turn any age list into any other age list, provided that we can come up with a clever type family and a type class that does the transformation indexed by the elements in the list. Is that clear? Does that make sense? I'm seeing nods, so that's a good sign. OK. Right. So we've just enabled this new kind in the type system. So we should probably check that we've not actually ruined soundness in any way. So remember before, we had this injective function, and we couldn't instantiate injective. So they couldn't instantiate the f argument of injective with a type family because of the saturation restriction. So that was the bit which protected type safety. Now, can we do it now? Because the saturation restriction is gone. Well, let's try. So like before, I'm going to try to instantiate f with a type family and say username, password. OK. So we get an error, but it's no longer this ad hoc saturation restriction error. This is a proper kind error. It tells us that expected a kind type arrow type, but db type has kind type squiggly arrow type. So we can have our cake and eat it too, basically, which is great. OK. Now, what about this expression, map maybe user? So why is it interesting? If you look here, our type family map takes a function a squiggly arrow b, which means that now we can map any type family over any list, which is great. But sometimes we don't want to map type families. Sometimes we just want to map normal type constructors. So when you're given a list of int, bool, and char, sometimes you want to map the maybe. type constructor. So you want to end up with a list of maybes of those things. The problem is that if we try to do that now, we get a kind error because expected a kind type squiggly arrow type, but maybe has kind type normal arrow type. Of course, that was the whole point of introducing this new kind, so that we can get these kind errors. But really, we still want a way to allow both mapping maybes and mapping type families, or DB types, say. So what's the solution here? And as always, the solution is to introduce a little bit of polymorphism into the mix. So the idea is, instead of having two arrows, the squiggly arrow and the normal arrow, we're going to have a single arrow, which is indexed by whether it's matchable or unmatchable. So we introduce this data type matchability, which is either matchable or unmatchable, and then here are the actual kinds of maybe and DB type. So they're indexed by, so in the case of maybe, we have type to matchable arrow type, and in the case of DB type, we go from type to unmatchable arrow DB type. And of course, these look quite ugly, so we can introduce type synonyms to refer to the respective instantiation of the polymorphic arrow type, so we get back the nice-looking kind signatures from before. But under the hood, now the arrow is a single arrow, which means we can finally replace this arrow with a matchability polymorphic arrow. So F is now an A matchability polymorphic arrow B. So that means it can take either a type family or a type constructor. And just to show that it actually works, we can now say, I need to reload first. Ooh. Age map. Okay, yeah. So I'll talk about this in a bit, but the idea is that now we need to provide this type signature. Cool. Yeah, so the whole thing is a single Haskell source file, which means that if I change something in this slide, there's a possibility of introducing a compile time error in a previous slide. It's the magic of live coding. Okay, so map DB type user. Still good. We can map DB type over user because GHC figures out that DB type has an arrow unmatchable in its kind. So it unifies M with that unmatchable, and it just works out. It also means we can now map maybe over this list. And in this case, maybe I'll scroll that up a little bit. In this second list, we say map maybe user, and maybe's kind, the matchable kind gets instantiated with, or sorry, with the M here gets instantiated with the maybe from, no, the matchable from maybe's kind. And so it works out. Okay. So now we have matchability polymorphism, higher order type families, all sorts of fun stuff. Now the question is, how does this interact with some other features of GHC? Because GHC has a really fancy, complicated, and cool type system. So I just want to give a quick taste of what's possible when you enable unsaturated type families and take into account all the existing features of GHC Haskell. So here's this type family, which I call everywhere. And the reason I call this everywhere is because it's going to apply a function f, which takes a b and returns a b, everywhere where it can find in some other type A. So what do I mean by this? Let's write the type family, and we'll see. So the first instance, I was going to, so we take the f, and we take some structure st, and we say, this pattern should match when the structure is of kind B. So GHC allows us to write kind index type families and match, so only match in a type family equation when the argument kind is what we expected it to be. So everywhere f stb, the b is part of the pattern, and to make it more clear what's going on, this equation matches when we're given a function that expects, given a function and an argument such that the function expects the argument, and in that case we just apply the function to the argument. So to show you what this does, when I say apply everywhere, apply the function plus 10. So I'm going to provide a type level natural number 10. It gives us back 20 because the argument, the function expects a nat, and we gave it a nat. If I say apply this function in the type level symbol hello, this instance will not match, so we have a stuck type family. This equation didn't match. Right, so when we have an equation that didn't match, we just write another equation that matches, so we have a fallback equation that says just return the structure without applying the function. Okay, so we can go back, say everywhere plus 10 on the nat gives us 20, everywhere plus 10 on hello just gives us back hello. Okay, now the crazy part. We can write an equation that takes a structure, and we know that the structure's type is not the type that we were expecting, but we know that the structure is a type application. So it's some type constructor applied to some argument x. And in this case, what we want to do is recurse. So imagine this. We have, say, st of x. Maybe that looks like maybe of bool. That's a type application. And what we want to do is recurse into both the maybe part and the bool part and see if we can find any interesting types there. So essentially, we want to apply this function recursively down the whole structure. So we first go into the left-hand side, which is the constructor, say everywhere f structure. And what we get back is, because everywhere takes structure A and returns to structure A, what we got back was, so what we passed in was a type constructor, and what we got back was another type constructor. So we need to provide it an argument, and that's another recursive call to everywhere. Right. Now, what this allows us to do is basically it looks at your type, deconstructs it into its parts, and recurses into it, and finds all the interesting types that you wrote a function for. So let's see. Everywhere plus 10 on 10 still works, but we can have a type level tuple of 2 numbers. Did that not work? Oh, yeah, thanks. The fact that compiled. Yeah. This is JavaScript at the type level. Okay. Right, thank you very much for that. We have a type level tuple of 2 naturals, and it goes into the type level tuple and finds all the naturals. And of course, we can nest this arbitrarily deeply thanks to recursion. So I can say I have a tuple of a natural and a type level list of type level maybes of naturals. And if all goes well, we get back exactly added 10 to every element. So it's quite a neat generic programming framework at the type level. It's scary that you can do this. Okay, another example, I'll go through this quickly, is higher kinded data. And I'm sure most of you have seen this pattern in production or on blog posts before. The idea is that we can define our data types. So the normal way of defining this record person is to just define it as 2 fields, username and password. The problem is, what if you want to have a partial version of this data type where some of the fields might be missing? You want to decorate it with maybes, or you want to have IO types in there. So the idea is to parameterize this person type with a functor where you take a functor f and wrap every field with that functor. Now you can do things like, what's the type of person, nothing, it's a person of maybe. How do we go back to the original type though? Because so if you use this higher kind of data type pattern, then you'll soon find that if you just want the normal version, then things get a little bit annoying because you introduce an identity new type, which simply goes identity A. And then you have to say, identity, I'll just do undefined, username, something. laziness. Okay, so the type of that is person identity, of course. But the problem is, as you saw, we have to wrap these fields with the identity constructor, and that's a little bit annoying. So what if we could say f actually doesn't need to be a type constructor. We can have any, we can have either type families or type constructors as arguments. So if I say that, then all the previous examples, of course, still work because they do. In that case, m gets instantiated with the right thing. What's the type of this type constructor? It's probably a string, isn't it? And I say this is a person of, oh, and then what? So we need a type family identity where the type family just returns the argument. Reload that. Great. So now you can write higher kind types, higher kind data types, where the functor you plug in is actually a type family. So you no longer have to wrap your fields with any identity new type or what have you. You can just say, oh, apply this type family to all the arguments, and those are the fields. And of course, it works with more interesting type families like, what's the type of, actually, you can do things like person db type, where every field will have the right db type field. So what's the type of person db type? Now this constructor takes a db text, and returns a db type. Yeah. Is the new type declaration obsolete now? You probably don't want to use it for situations like this, but there are still legitimate use cases for an identity new type. I guess maybe. Good question. Maybe it is obsolete.
In the implementation and the example that you just typed in, it's not using identity.
Oh yeah, it's not using. Yeah, so I can comment this out, and the example still works. Yeah. Yeah, right. So the example still works. Yeah, thanks. Okay. Oh, there are quite a few questions. Okay. Yeah, at the back. Could you make it a type synonym? Yes, you could. Oh, no. So there's I think, yeah, you should be able to, but I forgot to remove a panic, which checks that the type synonym is unsaturated. So yes and no. That's a good point, thanks. There was another question?
These decorated arrows with the curly braces, I haven't seen that before. Is that a particular extension as well?
Oh, so just to be clear, this is not merged into JC head. I'm running a fork of JC, and this is new syntax, and it's probably going to change by the time it gets into JC.
Okay, thanks.
Yeah. Yep.
Can GHC infer the type of person with that id type family? So what happens if you did person with no data constructor, essentially?
Yeah. So you mean if I didn't say that it was person of ID? Yeah, okay. So it would say that it couldn't infer what the type family is. And in general, it's really difficult to, when I give you the result of a function, it's really difficult for you to tell me what the function was. So GHC does not infer what the, so if you try to pass in a type family, you have to use explicit type application or type signatures. And that's actually my next point is about inference. And I'm not going to go into too much detail about how this works out. But basically the idea is that whenever you have this matchability polymorphic arrow, unless you say explicitly that you will want a type family there, GHC will default to a matchable arrow. So that is, it remains backwards compatible with all the existing stuff, which is the reason why it could just simply work out, in the previous cases, it could simply work out that I was interested in the identity. Of course, I commented out the, yeah. So I had a couple more slides on other interesting things, but those are not, yeah, talk to me in the break if you're interested in hearing about those. Thank you very much for your attention.
Thank you very much, Csongor. We're going to take a 15-minute break and reconvene in any of these 3